My today's topic is about the matrix representation, matrix representation of a linear transformation. Okay, matrix representation of a linear transformation, and is a very important topic, and the understanding of that is very, 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 very important. Okay, how to connect matrix uh, and how to connect matrix with linear transformation. Question is, why do we want to connect? Why do we want to connect two different things? Why do we want to connect two different things? That has to be two different things. That has to be clear to you. Why suddenly we want to connect a concept of something with a concept of another? It is because the answer to the given question is because so that the study of the answer, the reply to the question which has been posed by me is that so that the study of one reveals some characteristics of the other, So by the study of matrix, by studying matrix theory, we can uh, we'll be able to know something about the linear transformation, or by studying linear transformation we'll be able to know something about the matrix. Okay, sometimes the study of matrix becomes easier. So if we can get a matrix representation for certain linear transformation, then in that case it is possible for us to study that matrix, and we can get some characteristics, or something we can acquire we can gather some knowledge about the linear transformation whose matrix representation have been found. So therefore study of one helps us to study the other, and therefore we try to connect two different things. Now in the definition in the book, you probably have found that they have started the definition, they have started the section by defining ordered basis. Now what is that ordered basis? Basis? You already know that a vector space may have many bases. Say for example, if you want an example, I can set one for example, for R3, the three-dimensional space, one basis is this one, and another basis is this one. So, and there are many other possibilities of bases. So a particular vector space may have many bases. Okay, let us, for the time being, let us consider this space. Let us consider, without any loss of generality, let us consider the basis 1 0 0 0 1 0 0 0 1. Okay, So we are considering the basis of R3. Now we already know that this R3 is a special case of F3, where F is a field. F is a field that has been discussed several times earlier. Okay, so R3R is actually the special case of F3F. And in F3F, we actually define the basis. We try to define the basis of F3. We try to designate the basis of F3 by E1, E2, and E3, where E1 becomes 1 0 0, E2 becomes 0 1 0, and E3 becomes 0 1 0 0 1. So we actually give them a name, E1, E2, E3, like this, okay, for simplicity. These are actually the notations. Now what happens is that when we study set theory, and we consider the elements like, this is a rough work, okay, don't try to connect the thing with our current discussion. This is a rough work I'm doing to make you understand something, okay. So when we discuss a set and we consider a finite set like this, 1 2 3 4, so we name it as set S1, say. And if someone else gives us a set like 2 3 4 1, then actually we say that these two sets are same. So it is not important where are you putting the Millie, I know why you raised your hand. Probably I have disabled the chat. I'm not going to allow any of you to write anything on the chat box right now. Later at the end of the class, I'm going to enable the chat box. Then you can put your roll numbers over there. Because if some chats are coming, if you're continuously writing or something in the chat box, then it is actually distracting. So you don't have to raise your hand. So when someone capital S selects a set like a capital S1 1 2 3 4, and another person selects a set like S2 2 3 4 1, so actually we say that these sets are same. For the position of the elements is not important, we already know it. But this is not the case over here. In this particular case, what happens is that if you select the three items E1 E2 E3 in this manner, okay, and suppose this is your choice, this is choice 1, and another person is choosing the items, placing the items in this manner, E3 E2 E1. So this is our choice 2. So with respect to that, with respect to these choices made, we shall get two different matrices. For this I shall get a matrix which will be termed as matrix 1, and for this I shall get a matrix which will be termed as matrix 2. So these two representations will not be same. We are going to see it in this particular class. So here the positions actually matter. So therefore, but the main problem thing is that the main point is that whether you select E1 E2 E3, or you select E2 E3 E1, or you select E3 E1 E2, whatever you select, each of these are actually called ordered basis. Ordered basis. Why these are called ordered basis? Why these are called ordered? Let me talk about that a little bit. These are called, each of these are called ordered bases. Okay. These are called ordered bases because this ordered basis actually means, this ordered basis actually means, according to your book, it is actually meaning the finite sequence of linearly independent vectors, of linearly independent vectors that generate the vector space, that generate the vector space, that generate the vector space. Okay, so each of these generate the vector space. All we know that this particular set generates R3, this particular set is also generating R3, this particular set will also generate R3, because the elements present inside the set, they are same, E1, E2, E3, but the matrix representations will be different. Why we call it a finite sequence? Suppose, what is sequence? Sequence, you already know. Sequence is actually a function whose domain is n, whose domain is n, the set of natural numbers. So if we say, if we consider these three natural numbers 1, 2, 3, so 1 has got the image E1, 2 has got the image E2, 3 has got the image E3. That is a sequence. If we consider them once again, so 1 has got the image, for the second case it has got the image E2, for the third case it has got the image E3 for the second case, and for the third case it has got the image E1. So that is another sequence. For the third one, I can write it in the following manner. So you already know that these items can be arranged among themselves in 3 factorial, that is 6 ways. So each of these will become a finite sequence. Each of these will become a finite sequence, and therefore each of them will become an ordered basis. So that has been written over here. And also you have to know this term that out of them, if I consider a basis like this, E1, E2, E3, where the counting is actually the way by which we count the natural numbers. So 1 comes first, then 2 comes second, then 3 comes third. Then actually this, out of all these ordered bases, if we write like this, okay, the usual way of writing, the usual way of counting, that basis is called the standard ordered basis. The standard ordered basis. This is our, why it is called standard ordered basis, because this is the standard way of counting. You do not make the child to count like count from 1 to 10. You will not allow the child to count like 9, 8, 1, 2, 5, 6, 4, 10. Not like this. You give the child a sequence. Say from 1, then 2 things 2, then 3 things 3, then 4 things 4, like this. You keep on going like that. Okay, so that is the standard way of counting. So each of them are ordered basis. If you consider the standard counting technique, 1 comes first, then 2 comes second, then 3 comes first, that becomes the standard ordered basis. And in general, if I consider the Fn vector space, this becomes the standard ordered basis of Fn. This is the standard ordered basis of F3. And suppose if you talk about the polynomial Pnf, you already know these terms, polynomial of degree less than or equal to n, defined on the field F, then the standard ordered basis will be 1, then x squared, then dot dot dot, then x to the power n. This will be the standard ordered basis of Pnf. If you ask me, sir, give us any other ordered basis, apart from the standard ordered basis, then I can give you a ordered basis like this. This is an ordered basis. Okay, but this is not standard ordered basis. This is called the standard ordered basis. And standard ordered basis actually play a very important role in linear transformations matrix representation. I hope you have understood. Next is the definition, which I have moved on to the next page. The definition, let me write the definition first of all, because probably you are using your mobile phone, and therefore at the same time you will not be able to be online in Zoom and using your mobile phone to see the PDF file. It is not possible probably. Some of you may be using your laptop and desktop. This is not a problem for them, but those who are using mobile phone, so they are not able to see the page of the book. So for them I'm writing this definition. So actually, I know that writing the definition given in the book is actually killing time, but there is no other way out. I have to write it. So we have considered a basis, an ordered basis, not see the definition. For examination, I asked you to go with the definition properly, but so to when you read the definition, you have to be very careful. Don't say that see that I have not considered the standard ordered basis here. Any ordered basis will work in the definition. So here I have written only the ordered basis. So beta is an ordered basis for a finite dimensional vector space V. If you ask me, sir, what will be the thing about for the infinite dimensional vector space? So at least I can say that the Friedberg is a book where infinite dimensions have not been considered. Any mathematics on infinite dimension have not been considered. So do not ask me that question. Okay, let us remain let us keep ourselves in the domain of finiteness. So we have selected an ordered basis for x belonging to V. For x belonging to V, let a1, a2, an be unique. Another important thing, word, unique scalar, unique scalars such that this vector x can be written as a linear combination of this basis vectors. So I'm writing it as I'm writing it as this. Okay. Then this is the important part, most important part of the chapter, and which is also very applicable in quantum computing also. Okay. So I'm not going to talk about that because it will unnecessarily kill time. If you have any interest, you can anytime call me. I can discuss with you. So we define the coordinate vector of x, coordinate vector of x relative to beta denoted by x beta and defined as x beta is equal to a column vector a1 a2 an. That is called the coordinate vector of x relative to beta. That is called the coordinate vector x relative to beta. Now students, I'm asking you to, I'm giving you a suggestion. You just keep that suggestion in mind. This suggestion is a general suggestion. It is not related to mathematics. It is related to any subject you study. When you study something and when you have got your proper appropriate book, okay, be it any computer science subject or math subject or anything, try to stick to one book. Especially for mathematics, try to stick to one book. So suppose this, for example, coordinate vector of x relative to beta, this particular term has been denoted by this notation, x inside bracket and suffix beta is written. In some other book, suppose they have used another notation. Until and unless you are comfortable with that notation, use always this. I mean to say that always try to stick to one notation only. Do not get lost in the vast domain of the notations. Okay, so try to follow the concept from one book. You can solve problems from any book. First of all, I am going to give an example for the definition. It is very important what is definition is saying. So this until unless you give an example, this definition is not actually definitions not become clear to any of us. Okay, so let us put a definition, an example for the definition. Say for example, I am choosing R2. I am choosing R2, and from R2 I am selecting a vector. From R2 I am selecting a vector, like simple vector I am selecting say 1 comma 1. You know that 1 comma 1 is a coordinate point on the two-dimensional plane. So it is my x. Now I am considering now beta to be the basis 1 0 0 1. They have said that any ordered basis will work. I am choosing a standard ordered basis because standard ordered basis is also an ordered basis. So I can select it for better understanding. Now I'm going to express this x in terms of these basis vectors. So this, you know very well, this x1 comma 1 can be expressed as 1 into 1 comma 0 plus 1 into 0 comma 1. You know very well. So here in this particular case, this 1 is your scalar a1, this 1 is your scalar a2, and this is your u1 and that is your u2. Try to correlate the things. Okay, now if you ask me what will be the coordinate vector of x, relative to this basis beta in this particular case, then this coordinate vector will be 1 comma 1. So you see, so many representations you are getting. What you are getting actually, initially when we were in school, we used to call this one point, we used to call this point as 1 1, and that is, we used to call it as a vector 1 1. Initially we called it a 1 1, a point just with a point 1 1 coordinate. Now when we started studying the vector space, we began to call it as a vector starting from the origin, goes up to the point 1 1 set in the two-dimensional plane. And now what this matrix representation is saying, this vector, let us name this vector as v. This vector v is similar to the coordinate 1 1 in coordinate representation, is similar to matrix 1 comma 1 in matrix representation. So all these things are actually same, different representations, different items. Just like when I teach linear algebra, you call a particular teacher takes the class of linear algebra, you say that this is a linear algebra teacher. And when I am taking the class of statistics, you say that you have forgotten my name. You say this is our statistics teacher, and this is our physics teacher. This is our chemistry teacher. This is our quantum mechanics teacher. This is our classical mechanics teacher. Maybe the same person. So you try to, in different domain, you give him a different name. So here also same thing are getting different names in different domains. In the coordinate geometry, we call it 1 1. In point, in vector space, we call it a vector. In matrix representation also, we call it as a matrix. So but it's interesting to know that we do not consider the row matrix, we consider the column matrix. Okay, column wise. So it is a column vector actually. This vector is a column vector. Now this is the definition which is very important. One example is written over here. One example they have set in the book. They have considered the vector space P2R. We know that this is the vector space. This is the vector space of all polynomials of order of degree less than or equal to 2. Okay, and its basis is all polynomial of degree less than or equal to 2. So its basis will be 1 comma x square. And this is not only the ordered basis, this is the standard ordered basis for P2R, standard ordered basis. Now if you consider any vector from P2R, we are considering any vector, let v be any vector of P2R, then we can consider this vector v to be as a representation of some multiples of some multiples of this basis vectors. So they are choosing, in the book they are choosing 4 into 1 plus 6 into x minus 7 into x square. So in their case, this is your a1, this is your a2, this is your a3, and this is your u1, this is your u2, this is your u3. Okay, and now if someone asks you to write the coordinate vector of v with relative to the basis beta, beta prime, say, let us name it as beta prime. Okay, to distinguish it from the earlier problem, then this will be what? The column vector 4, 6, minus 7. If you ask me why don't they take the why don't they take the row vector, why do they take the column vector, then I must say that this is done. Actually, the first point is that the way it has been defined, this is the way by which it has been defined. The second point is that they do it by keeping in mind a broad perspective. That broad perspective you are going to get from today's class, if I get chance of discussing, because this discussion takes a considerable amount of time. So if I am able to give you that broad perspective, then you will get to see why it is actually the column vectors are taking. For instance, for now I can only say that it is taken because so that we can easily multiply by the two matrices. Okay, so that is the reason. So you have to be very much careful about this definition. So suppose you are sitting, suppose this particular topic is there in your examination syllabus, then I must say that you have to read this definition very carefully. And what are the important points? What are the important parts of this particular the definition? This is one important part, that they talk about any ordered basis, not only standard ordered basis. Then a finite dimensional vector space we have to consider. We don't know what will happen in case of infinite dimensional vector space. And the scalar representation, this is unique. It's not true for any scalars. So if you want to represent a vector with respect to these basis elements, then these scalars, choices of these scalars must be unique. Okay, so if you want to express this 1 1 with respect to these basis vectors, then this scalar must be 1 and that scalar must be 1. If you change this scalar 1 and 1, if you put any other scalar, then the coordinate will change, the vector will change. So therefore this word unique is very important. Actually in mathematics, what happened, whatever we do in our real life, we try to give it a name, we try to give it a I mean a representation, and that representation is done by matrix. Suppose what is the actual why do we study mathematics? Applications do come after. Does the applications come after the mathematics? No, it is not true. First the application comes, and then once we see the applications, then from that application we try to generate the mathematics, because we are seeing only one part of the application. We do not know what will happen if we put this application to other system. So if we want, and possibly it is not possible for us to put the application in other system, then we want to guess it. You can only guess, you cannot dream of that. No, it's not a magic. So if we have a defined domain, we can guess that if I put this particular thing to that system, it will work like that. Okay, so just like in physics class, people say that, okay, if you, in friction theory, if you take a ball to the hill and you just leave it, the ball will roll down. Have you ever been to the peak and rolled the ball in that particular way? No, but you can imagine. Yes, this is the thing. That is the theory. Ball rolls, thing slides. That is from there they have defined the friction, the theory of friction. So that's how you imagine. It helps you to imagine things, define things which has not been experimented yet. Okay, I actually wanted to do a particular problem in this session, but this session timing is actually, the countdown has already begun. So in the next session I am going to do that exercise. For the time being, no, I cannot okay, I am actually pausing over here, so that only 3 minutes 22 seconds left. If you want to ask any question, you can ask me now. I am enabling the chat box so that you can put your attendance over here. the next phase of discussion is going to be happen in the session 2. Okay. Now